Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning.
Hello, class. I hope all of you are doing well. So I got everyone's response, and all of you did a great job on figuring out what it was the horizontal velocity of the projectile based upon knowing the height and also the range that it landed. So now we're going to do part two, and this is going to be the fun part. So let's first kind of recap what you've already done before. Okay, so we have a cart going down a ramp, and in the process, we found out we measured where did it land, so what was the range of it, and also measured how high was the ramp. And just from those two bits of information, we can find out how fast was the cart going here. So these were the measurements. It was going 0.545 meters was the range of it, and the table was 0.655 meters above the table or above the ground. Then, using that information, you're able to figure out what was the horizontal velocity. And now, what we're going to be doing is we're going to be raising this up and find out where is it going to be located, and then also find out what is the new range, the horizontal distance of the hoop, and then also figure out how high up will the hoop have to be located, and then also what is the angle of it. Okay, so let me just kind of recap this. So now we're ready for part two of this lab. So let me go a little bit more detail as to what's going to be involved. All right, so this is the setup. I'm taking the same table, the same ramp, and put it on top of another table here. So I measured what was the height of that table, and it came out to be 1.38 meters. As you can see here, I end up cutting off the inches because who wants to use inches? So as you can see here, the ramp, or the bottom of the ramp here, is 138 centimeters, which is 1.38 meters. And also, all of you end up getting this answer, something very close to this. Some of you may have gotten like 1.47, 1.5, somewhere around there. When I calculated here, I got about 1.493. Just use whatever you end up having here, or if you want to use this value here, that's fine as well. So from that information, again, we're going to find out what is the new range of the projectile. Now you have to keep in mind here, this is a projectile, and projectiles follow a very specific type of path here, which is called a parabola. So it has a parabolic curve to it. What you have to do in order to find out the range of it here, it's not traveling in a straight line straight down here. It's following this type of path here, which is going to be important when we start looking at the placement of the hoop. All right, so based upon this information, the table is 1.38 meters above the ground. Gravity is still acting at 9.8. Vertically speaking, it's acting as though it's being dropped. So it has no velocity vertically speaking. Okay, so it'd be no different than me taking a projectile or taking this car and 1.38 meters and then just dropping it straight down. So the first thing you need to find out is how long will it take for it to hit the ground. So that's the amount of time. Now the amount of time it's falling is also the same amount of time that's moving across horizontally. Now this time you now know what is the horizontal velocity, 1.493 meters per second, or whatever value you end up measuring here. So using this time and using this velocity, you're now going to solve for what is this distance? What is the new range of the projectile? Okay. Now whatever you do, just because I increase it by a certain height, and this is a common mistake some people make here, is they think, well, basically if you were to double the height, I should double the range. That does not work. Okay, that would only work if the path of it was basically a straight line down. But because it's following a parabola, that does not work. Then, next thing you need to do is whatever distance you have, I want you to cut that in half. And this is where we're going to be placing the hoop, is halfway in the path of its range. So if the car is supposed to land here, I want the hoop halfway in between there. So again, whatever the distance is, whatever the range is, just cut that in half. So when you cut it in half, you're also, what you do is cut the time in half. In other words, the amount of time for it to fall down and also the amount of time for it to go across, that's also the time that will be crossing this midway point. Okay, think about it this way. If you're traveling 50 miles an hour, and if you travel for 50 miles, it will take you 1 hour. Well, if you're traveling half that distance, 25 miles, it will take you half of an hour. So the same thing is happening with this. If you're traveling horizontally speaking, if you're traveling at a certain speed, you will have traveled a certain distance within that time period. So if you're traveling half that distance, you're also going to be traveling for half that time. So you'll need this half time as well, and you're going to be needing that here a little bit later on. So again, you take your range, cut that in half. But also, technically, you'll also need to split the time in half, and that's the time that you're going to be crossing this midway point. Now, using that half time that you end up using here, this is now you need to figure out how high up do you have to place the ring. And you can't place it halfway. Again, that would only work if it's falling down at a straight line here. But because of a parabola, this would not work here. And even though this is not drawn to scale, you can kind of see that this does play a factor here in the fact that even though horizontally it's half, vertically it's not. It's far from it. So, knowing this half time, there are several things that you can use here, using these formulas down here. What I want you to do is tell me how high up must I place this ring. Now, the thing is, the calculation that you're going to be doing here first is you're actually going to be finding how far would it drop. So, using this half time and using the formulas here, treat it as though you're dropping an object straight down. As though the initial velocity is 0. And so if you know the time for it to fall down at this point right here, you can find out how far did it drop. Now, because you also know how high the table is from the ground, it's kind of difficult to place the ring based upon here. It's a lot easier to go from the ground on up. So what I want you to do is the hoop height based upon the ground. So all you have to do is just subtract these two values here to give you what is the height of the ring from the ground. Okay, so again, you're going to use the half time and find out how far would the car drop, and then using how far would the car end up dropping, and knowing the height of it, you can find out how high up must the ring be placed. One other bit of information I want you also to solve for is what is its vertical velocity. And you're going to be using that a little bit later on. So when it's at this point right here, let me draw this here. So when it's at this point right here, I want to know what is its vertical velocity at that point in time. Okay. Now when it's down here, that vector is going to be a lot longer. I can't draw it based upon the room I have here. But I want to know how fast is it going to be traveling vertically at this point right here. And again, treat this as though this is an object just being dropped down where the initial velocity of this is equal to 0. Yeah, okay, pretend that's a 0. So treat this as though this is an object falling for a specific amount of time that you see over here. Okay. Now, so that's where we're going to be placing the ring. Now, one other bit of information. If you know horizontally, the horizontal velocity of the car should remain constant, or ignoring wind resistance, it should be constant. And also because you know the vertical velocity from the previous part, by knowing those two vectors, you can now solve for what angle will the car be traveling, and also what will be the resulting velocity of that car. So it still going to maintain its horizontal velocity. At this halfway through its flight, you're going to find out its vertical velocity, and then from that you're going to find out its resulting velocity. And this vector here is tangent to this arc. So I want you to tell me what is the projectile's v sub y, this value here, which we will solve for the previous part. What is the resulting velocity? And then also, what is the angle of the car? So at what point, when it's right here at this halfway point, what angle is it traveling here? Now, that's going to be important for this next part, because that is the point where it's going to be passing through a hoop or a ring. And so if you know the angle which the car is going to be traveling, if the ring is horizontal, it should be able to pass through it, but there's also going to be, that's not the max amount of space that the car is able to pass through. To give it a better chance for it to be able to pass through that hoop, it would be ideal for that ring to be perpendicular to its path. So the one thing we have to do is also angle this ring up. And so if you know the angle of that hoop, this right here is going to be perpendicular of what it's actually going to be traveling. So if you have, kind of picture like if you have like a basketball hoop, basketball hoops are always going to be horizontal. The problem is that when a ball is coming in at an angle, if it comes in at too shallow of an angle, let me see if I can draw this here. Kind of picture this is a basketball hoop, and you have a ball that's coming in this way. Let's pretend there's no backstop to it. As it comes in here, it's not going to be as easy for it to pass through unless the hoop is more like this, perpendicular to its path. Okay, so, or even if it's at a, let me draw another ball here, and let's say it's traveling this way. Oh, I'm sorry. Let me try that again. I'm just drawing a bunch of circles here. Say if it's traveling at an angle like this, ideally you would like to have the ring to be perpendicular to that path. Okay, so hopefully that makes sense. So again, you're going to tell me what is the v sub y, what is the resulting velocity, what is the angle the car is going to be traveling, and what angle will the hoop have to be placed in order for it to pass through. And all you have to do from here is, because this is going to be perpendicular to it, 90 degrees from it, is that if you take the angle of the car, subtract it from 90 degrees, that will give you the angle to which the hoop is going to be placed. And a lot of times we end up using is like the app on the phone to measure the angles. So if you measure from the horizontal and then raise it up so many degrees based upon this calculation here, that should be the point where this path right here is going to be perpendicular to the ring itself, which would then maximize the amount of space of which it's going to be traveling through. And the hoop it's going to be passing through here is roughly about 2 to 3 inches. So it's not going to give the car a whole lot of wiggle space here for it to be able to pass through that ring. So that is your task. I'll put the due dates for that. So wherever you see the question marks here, that is what you will need to figure out. So again, let me just kind of back up here. So this is the setup. So the car, you already have the initial velocity. You're going to find out what is the range of the car. Okay, so you've given me this answer. And when you do this, take a picture, send me the picture, and then also have these things labeled and boxed in so I can tell what is what. And then what is the horizontal range of it, where you're going to be placing the hoop, and also what's going to be half the time. And then what is the vertical height, the vertical height that the hoop has to be placed. And then tell me what is the vertical velocity of the car when it's halfway through to its flight, when it's passing through the hoop, what is the resulting velocity, what is the angle of the car as it's passing through the hoop, and then what angle must we place the hoop to give it the best chances for it to pass through that ring. Okay, so hopefully that makes sense. And again, show me your work, box in your final answers, make sure you have these labeled, and once I get everyone's results, I will go ahead and set up the car and the hoop and everything according to your calculations, and we'll see what type of results we end up getting. Okay, so if you have any questions, please let me know. I hope all of you are doing well, and you guys take care. Bye-bye.